Hi, my name is Miloš, welcome to Element 14's Robotics 101 Part 2. Last time we talked about electronics, mechanics, and what is a robot. This time we're gonna talk about control engineering and the robot operating system. Last time we talked about electronics, we talked about actuators, we talked about sensors, we connected some of them to a microcontroller, closed the loop, and that's all of the things that we're gonna continue talking about in this video, but we're gonna take a different approach. So last time we went from the hardware side of it, this time it's gonna be software. So we talked about microcontrollers, we also programmed an Arduino, and this time we're gonna talk about both microcomputers like this single board computer, which is a Raspberry Pi 4, and also microcontrollers, and see what software goes where, why some software is meant to go on a microcontroller and something needs to go to a more powerful thing like this, and so on. Let's look at the bigger picture of our robot software architecture. We are starting with our mobile platform. Physically, it is equipped with 2 drive motors, and we will add other stuff as needed. For this hardware to actually be useful, the robot needs a task. Let's give it a classic robotics challenge, navigating through a maze. To pull this off, the robot needs some sensors to figure out where the obstacles are. For example, we can use 2 wheel position sensors called encoders so we can measure the robot's position and speed, and a 360-degree LiDAR sensor to measure the distance to the obstacles. With the hardware figured out, our robot needs to figure out where to go and what to do with all of that data. We need some kind of a path finding algorithm. For this, we will use a rather simple one, where we will just want to keep next to a left wall at all times. This means at every intersection we take a left. By continuously reading the walls, the robot uses that simple rule to generate a successful path from the entrance all the way to the exit. Making that physical movement happen requires a specific stack of software blocks. At the top, we have the control interface, which is our graphical user interface. Next is the path planning, which handles our edge following algorithms or AI, for example. Then comes sensor fusion, which uses math like Kalman filters to combine our LiDAR and wheel data. Finally, at the lowest level, we have sensor readings and actuator control. These software blocks have vastly different hardware requirements. The higher level tasks, the interface, path finding, and fusion, require heavy computing power. They process a lot of data slowly and are not strictly timing critical. Therefore, we assign them to a single board computer like a Raspberry Pi or an NVIDIA Jetson Nano. The bottom level tasks are exact opposite. Reading raw electrical signal and pushing power to motors requires lightning fast millisecond level precision. An operating system running on a standard computer will interrupt these signals, so we hand these strictly timed tasks over to a dedicated microcontroller. Looking closely at that actuator control block, this is where we dictate the exact speed and position of the wheels. We achieve this precision using PID controllers. Because this is the absolute foundation of getting any robot to move accurately, we are going to start right here. So PIDs, why are they so important? If you haven't heard of that name before, PIDs stand for Proportional Integral Derivative Controllers, and they're the controllers that, for example, on this robot here, ensure that all of these robot joints actually move to a certain angle and keep that angle, or if we look at these wheels, it ensures that they either move a certain angle or that they're moving at a certain speed. Now, the thing with PIDs is that they're extremely timing critical, so we need to run them at lower level hardware, meaning microcontrollers, and to get them as fast as possible. So we're talking about millisecond or microsecond level precision, something that we can't achieve with single board computers like a Raspberry Pi. How do they actually work? Well, I'm gonna show you that now through just a bit of math, don't worry, and then we're gonna see a practical example with this board here on how we can actually, what's PID tuning and how they work, to see if we can achieve some good results in controlling a motor. Also, if you want to know more about this board, this is an open source project that you can also check on Element 14 Presents, which is a dual motor driver if you're more into electronics and motor driver side of the things. So let's go and figure out what PIDs are. Let's take a look at how a PID controller works. PID stands for Proportional Integral Derivative, and I'll get into the specifics of each one of those later. So let's first imagine the PID controller as a black box with some inputs and outputs. 2 inputs, so reference and a sensor, and just some kind of an output signal. In our case, we will give it a speed reference, the speed measured by our encoders, and a PWM duty cycle that will go to a motor drive. But what's actually happening inside this black box? So here is the diagram of that. We have the 3 components Pi and D, we are summing them and getting them to the robot or to our actuator. We are reading the encoder signal, then in a piece of code we are converting that signal to the speed measurement, and then we're subtracting that speed from our reference, getting our error signal. The idea and the purpose of the PID controller is to actually minimize that error, ideally to have it at 0. Now let's take a look at each component of the PID controller. So as I've said in the beginning, we have the proportional part, the integral part, and the derivative part. The proportional part is the simplest one. This part adjusts the output based on the gain and how far you are from the reference. So you can imagine if you want to go at 100 kilometers per hour and you're going 50, for example, you're gonna press the throttle more than if you were at 8. Integral part of the controller works by using the integral gain and the accumulator is just the sum of all of the errors so far. It really helps with correcting the steady state error. So for example, if with the P controller you get to around 95, the integral part will get you just right around to the 100, as you will see later on in the video. And in the end we have the derivative part, which works with how fast the error is changing, and that helps with overshoots. The actual output of the PID controller is the sum of these three components and is represented by this formula here. Now, this is just some random math now on your screen, so I'll try and draw you a graph to get this a bit closer to you so you understand how it works. So here is our graph. The yellow line is a reference, so we just want at some point our speed to jump from 0 millimeters per second to, for example, 10 millimeters per second. Doesn't really matter the number. Ideally, our controller would follow this reference completely like this with 290-degree turns, but that's impossible, as we will see. So let me first draw how a P controller would look like. It would be something like this. And as you can see, it increases the speed when the reference jumps, but it never actually reaches that reference. There's always that steady state error. Now, if we added integral part of the controller, we would see something like this. The signal would rise a bit faster and we would have no steady state error, but you can see that we have a bit of an overshoot here. If we added the derivative part too, and this is of course if everything is properly tuned, we can then lower that overshoot and get a controller that follows the reference much better. And when I say tuning the controller, that just means adjusting the proportional, integral, and derivative gain and see how your output looks like. Now, because of non-infinite acceleration, you can never get an ideal controller that follows the reference, especially for step references, but they work really good, especially for real systems, and I'm gonna show you an example of how this works with our actuators. Now it's time to see in practice everything that we've just talked about PID controllers. On your screen now you can see a small DC motor that has a magnet on top, and it's pointed directly to this little board that has an encoder on it that detects the field from that little magnet, and that's how it tells the position. So all you need to know for now is that this sensor somehow gives us the angular position of this motor, and we'll cover more and we'll talk more about types of encoders in the next video. And here on the right, the blinking green thing is my own custom PCB for driving brushed DC motors, and there's a whole video on Element 14 Presents on how I designed this whole thing if you want to check it out. But now, one more thing that I did with this is design a software or a graphical user interface for controlling this motor and for also PID tuning, and we're gonna jump into that now. So this is the interface. We can select this port, connect, and at this point we're connected to the PCB and we can control the motor. So for example, if we enable this bridge and click drive, you can see that the motor starts driving in one direction, we can change the speed and so on. So this is where we're gonna do some PID tuning. First, let me turn on these reports so we can see the data coming through. And we need to do self-check direction, like so, to know if the motor is spinning in the direction that we want. And now we can go to the closed loop section. So in the closed loop section, we have two different PID controllers. We have a speed and a position PID controller, and we'll begin with the speed one. So here at this part of the screen, you can adjust all of your gains. And for example, let's put something that I know should work probably nicely. I'll just reset and zero the position, change this to speed and this here to speed as well. We can also clear all of the old data. And now if we click speed PID and apply mode, now we're in speed controller mode. So currently the speed of the motor is 0. You can see some noise, but that's just because of the noise floor. So for example, if we put 1000 here and said click reference and also enable the driver, you can see that the speed is starting to pick up. And if you take a look at the motor, you can see that it's slowly spinning up, which is what we expect. 1000 counts a second is about a quarter of a turn a second. So if we go 4096, this is 1 turn a second. So let's try that out. And you can see how the PID is trying to reach it. But now you can see that the gain isn't the proportional gain isn't strong enough because it's a bit slower and so on. But if we pause and take a bit of a better look here, we can zoom in. You can also see that we're not able to follow this reference ideally because the reference is rather sharp, and we'll talk about that more a bit later. But essentially this PID is not tuned that bad, since there are some other limitations that I have, like the frequency at which this thing is going. Also on the right of your screen here you can see some oscillations. So yeah, there's also that limitation of the actual system. But let's see when we do some other kind of values. For example, if we put the gain, the proportional gain to be much higher and apply, you can see the massive oscillations that we begin getting here. And that's because the system is unstable. So let's tune it back down to 0.1. And you can see that we're again reaching the steady state rather nicely. We can of course change the reference, let's say to 8000. The motor would speed up to -8000 and so on. One thing you might also notice is that I'm only using proportional and integral here and not using the derivative. That's because putting any derivative into this system will just make it really noisy. So I decided to keep it at 0. We can also just have 0 for the integral part as well. But then if we, for example, go to, let's say, 4000, so you can see better, and set that reference. And let's just let it try to reach the steady state. Pause, and if we come here, this is what you've seen in the drawing. So the controller tries to reach the set point, but it never reaches, and it never will reach it, like so. But if we add just a bit of integral to this, and click the continue, you can see how the speed is starting to slowly climb up towards our steady state point. And that's the tuning of the speed PID controller. So what about the position one? Let's first reset everything. Go to position here. And let's go to position and apply. Clear data, clear data. And so we're at around 0 degrees currently. You can see the current position here. And if we put, for example, 360 degrees, so for the motor to do 1 circle, and click send position, what will happen? You can see how slowly the motor is starting to spin. You can see it spinning slowly, and it's trying to reach our steady state of 360 degrees. You can take a look at it here. It's really in slow motion. This is because the gain is just not enough. Of course, this is something we can change. For this setup, it would be more around 10. And you can see how it just jumps up. So if we go back to 0 degrees and click send, you can see again how quickly it goes. And for example, for this position controller, even just the proportional gain is rather nice. If we take a look at this here. Yeah, rather nice. So let's continue here. Though it doesn't hurt to add a bit of integral part as well, it just follows the reference nicer. So if we go again 180, send position, you can see how quickly it reaches the position, 360, minus 360. You can hear it how it spins up rather quickly. So yeah, that's working rather nicely. We can also pause here and take a look at, for example, this part of the data. And one thing you'll notice is how we're never able to follow this line perfectly. And we'll talk about that in the next part of the video as to what's actually possible in reality and what's theory. I hope PIDs are clear and that you liked the demo that we did with this board on PID tuning. And if you have any further questions, feel free to leave them in the comments, but you've also seen some limitations, and that's where theory and reality kind of crash. In theory, we would love to have those step reference curves. For example, if we have this robot here and we want it to start moving from 0 to 1 meter a second, we would just want it to go instantly to that speed, but that would require actually infinite acceleration, and the main thing with reality, nothing infinite is possible when it comes to those physical things. Also for this robot arm, we would love it if we wanted the robot arm in this position. We would want it to just jump from this position to this position without caring what's happening in between. But what's happening in between is actually really important because we're interested in how that robot gets there. So we need to look at all of the motion profiles. And that's what we're gonna discuss next. We've seen how PIDs work, but to get true precise control, we have to bridge the gap between pure math and physical reality. Let's use a relatable example, driving a car. You're cruising at 50 km per hour and pass a speed limit sign for 80. In a purely theoretical ideal scenario, your speed would instantly jump from 50 to exactly 80 the millisecond you pass the sign. But we know that's not how reality works. You actually start speeding up gradually until you reach 80 km per hour and then you maintain that speed. To understand why, look at the formula for acceleration. Acceleration equals the change in velocity divided by the time it takes to change from one velocity to the other. If we want our speed to change instantly, our time is essentially zero. Dividing by zero means we would need infinite acceleration, which is physically impossible. This is the exact same struggle we saw earlier when we fed a sudden jump to our PID controller. Simply put, no sudden changes are possible in the real world. This means we can't just send raw target numbers to our motors, we have to send them a planned shape over time known as a reference profile. The first is the square or step profile. As we just proved, a motor simply cannot follow this in real life. It will lag, spike in current and struggle to catch up. To fix this, we can use a trapezoidal profile. Here we ramp the speed up over a set amount of time, hold it and then ramp it down. So if we want an equivalent of the step, it will just be a ramp. This is much better because of our time is no longer zero. However, it is still not perfect. If you look at the acceleration graph for this profile, it still demands instant jagged jumps in acceleration at the corners. So while much closer to reality, this exact shape is still not possible. To get a truly smooth, realistic movement, we use an S profile. By smoothing out those sharp corners, we create a reference curve that our motors can actually achieve without violently jerking the robot's hardware. But remember, even with the perfect S curve, we are still bound by the laws of physics. The slopes of these curves can never be steeper than the maximum achievable acceleration of your specific motor, and the top of the curve can never exceed its maximum speed limit. But if we play within these ranges and try controlling the motors and accelerations and speeds they can achieve, we can get a nice match between theory and reality. Let's see this in practice. Like last time, we're back in the graphical user interface. We have the motor at the bottom right of your screen, and now we're going to look at curves. So as you've seen in the PID tuning and generally in the drawing, following curves like this, which is essentially a square wave, it's pretty impossible in a real world scenario, and that's what we're going to show here. If we just reset the loop and zero the position and click start playback, you will see what will happen. Let's let it do a few iterations here. Even when it's not zoomed in, you can see the issues here, but let's let it do a few more just to see that this first one was not a fluke. And this is a rather nice tuned PID, not perfect, but more than okay for something like this. And let's just let it go back, and we click pause here. Okay, so we click stop playback, And now we can zoom into, for example, these first two. And here is the issue I talked about. You can see that no matter how fast the motor is, it can never be vertical like this line here. Let's even zoom in more. You can see that when you zoom in more, this is just the delta between 2 points. You can see how much slower this is. Let's reset the view and go back to a whole square wave. And you can see the same issue here when we're going back the position. So this is just not ideal for motor. This is something that we can make in reality, like in theory. We would love to just be able to teleport from one reference to the other, but that's just impossible. So the other option would be to use a trapezoid. Let me just copy that curve real quick. I've already calculated a few curves and we can just paste them in here. We can preview the curve and this is how it would look like. And maybe we can even speed it up a bit. You can see the seconds here. Click preview curve. That's looking good. We can click continue and let's click start playback. Even that was a bit quick, but we'll see how it looks. Okay, let's maybe speed it up. Let's maybe slow it down a bit to 150 preview. And let's play the new curve. Let's wait for it a bit. And then it will start going down. Back up again. And back down again. So let's stop that, pause this, and let's zoom in to see what's going on. So as you can see, this is already looking much better, especially since even the reference here is not perfect. This is just to show you a bit. And yeah, this is rather nicely, but when you have a sharp change, especially when you get into more capable systems than this motor and at much higher PID frequencies, you would have something called a jerk here, where you would want a sudden change in acceleration. Maybe we can see that more clearly if we speed up again. Let's say 50, preview curve and start playback. We will see how this will look now. I mean, it's still better than the square wave, but it's far from perfect. Let's just wait for it to go back down. Click stop. We can pause here, and if we zoom in on this central one, you can see that the edge is rising much faster than we can follow it, and vice versa here. When it's falling, we can't really follow it that quickly. This is also because we could follow it at slower speeds. That's because the maximum acceleration of our system could actually handle this, and here we can't handle that, and that's why there's a gap here. So that's the talk about those absolute values that we had in the drawing. And in the end we have the S curve. Let's copy that. This is the ideal scenario that you want to have. Preview. And let's just mirror it so we can get essentially like impulses, and maybe slow it down a bit. Preview here. Click continue and reset loop, 0 position, clear data, and start playback. You can see that even this is too fast sometimes in the beginning, but this is an ideal case when you want to go from a reference to a reference. You can see how much more nicely we can follow it, since the motor needs a bit of time to start up and to also slow down. So this is looking much nicer if we stop the playback once it gets back. Let's stop it right there and pause the data. Let's zoom in, for example, on the first one. You can see how much more nicely it follows it. There's a bit of difference here, but that's due to the reference resolution, and maybe the system is not fast enough in this middle section, but yeah, much nicer than the square wave definitely and the trapezoid. And we can also, I mean, this is not the only type of reference you want. Sometimes maybe you want a sine signal style reference, something like this, where we just don't want the mirror. And yeah, let me put 40 here. That should be okay. Continue and start playback. And if you also take a look at the motor as we are talking about all of this, you can see how nicely we can follow slowly changing curves like sine waves and S curves. So the whole idea is to get these two to match so that you can't tell them apart. The closer you get them, the more precise your robot is gonna be. If you're only having like square waves for changing references, for example, imagine that on a robot arm, in all of those transition states, you won't have a clue where any of your joints actually are. And when you finally tune your PID and get a much softer curve like this sine wave here, you get really nice following results. So yeah, that would be the talk about curves, and one way that we're gonna use this actually in the later videos is when we want to follow some kind of specific reference. We can always do something like passing the recorded reference for a low pass filter so we don't have any sharp edges and get something nice that our system can follow like this. With that, we've covered everything we need to actually control this robot arm for now. So we know how to actually program the motor drivers to actually go to certain positions. And now we know that it's important for each of the motor to send them realistic references, especially when we have a bunch of them coupled like this, so we can get the movement that we're expecting. Just imagine if we want this tip to move straight up, it would need to go somewhere like this, and you see how all of the motors moved in unison. Now for the arm to get from this position to this position, we have also done this. And maybe it would have done that if we just gave it random references, but if we tune everything nicely, we can get those smooth movements and control it in space and also time. So yeah, that's all of the things that we will need for now for low-level control. But what about high-level control? Something interesting about this arm is, and we'll talk about it more, how you find where the actual point is direct kinematics and how you find the angles of all of the joints dependent on the coordinates of the actual end effector is called inverse kinematics. And that's actually rather heavy computing, and for that, while microcontrollers have gotten rather good even for a calculation like that, you would probably like to use something like this, which is a single board computer like a Raspberry Pi 4. You would calculate all of the angles that you need based on all of the parameters. You can even have AI models, anything you would like. And then you would send all of those commands to a microcontroller so it can do all of the low-level stuff and control it. One thing that I mentioned at the beginning of the video that we're going to cover now is called the robot operating system. So what's that? That's a middleware, so it's not an actual operating system, but it's a really nice framework for developing robotics project, and that's because it lets you have code in modular segment called nodes. Each of those nodes, imagine like a single Python script, for example. It can communicate between nodes using topics, using services, and other things that you will see now. And the idea with this is, for example, if we have this and this, as you will see, so a computer that has robot operating system on it and a microcontroller, you would have one node that just does communication with this, and then you would develop different control strategies, for example, and you would never have to repeat the code that just communicates. You would know always it works. It's also a really nice and easy solution for adding new sensors or deleting something and knowing that the whole project won't break. So it's a really nice and modular system. So let me explain this in a bit more detail, and then we're gonna test it out like we did with the previous two things. Let's bring everything together using the Robot Operating System, or ROS. While there are differences between ROS and ROS2, the concepts that I will show here are true for both cases. Let's go back to our little robot trying to solve the maze. This block diagram nicely illustrates the setup that can be expected on this kind of robot. We can have two microcontrollers where one will be working with actuators and their sensors, and maybe another microcontroller handling another set of sensors. Connected to them will be a Raspberry Pi 4B running ROS2 Humble. It will communicate with the MCUs over, let's say, USB and I2C, and the MCU1 will handle all of the PIDs that we've covered in this video. Let's see what the ROS setup would look like software-wise. Instead of writing one massive complicated script that controls the entire robot, ROS allows us to write small independent modules of code called nodes. Node 1 and Node 2 run in continuous loops as all of the other nodes. Their only job is to send and receive data to and from our microcontrollers. This is really handy because it means once we get that communication right, fully tested, we don't have to touch it again. This also means that if we want to add another different microcontroller, we will just make another node. For this robot to work and actually solve the maze, we need higher level logic. So we create node 3, our left edge path finding algorithm. Looking at it like this, these nodes are just separate parts of code all running in their own loop. But here is how we connect them in ROS to work in unison. These nodes communicate through a publish and subscribe system over channels we call topics. Imagine topics as communication channels to which any of the nodes can subscribe or publish. For example, we can have a topic for sending commands to the actuators and a topic for getting motor data, and we can also have a sensor topic from the second node. When they subscribe, they can listen to all of the data coming down that topic, and they can also send data by publishing to that topic. The topic is also defined by the message. We define that message to our needs as many fields as we want, so that all nodes know how to format the data when publishing and what to expect when they are subscribed to that topic. For quick one-off commands like updating a parameter or reconfiguring a sensor, nodes can also communicate using a direct service call, rather than a continuous stream of topic data. Topics are expected to come at a certain rate continuously, while for service calls they are ad hoc and are also followed by a response. This response is extremely useful because in that way you can get a confirmation whether your service call has been successful or not, and also get some results back. We can finally let our robot loose in the maze now. With this left edge algorithm running, our robot successfully navigates the maze by hugging the left wall, shown here by the green path. But here is where the true power of ROS modularity comes in. Let's say we want to completely change our navigation strategy. We can simply swap out node 3 for a brand new node 4, a right edge pathfinder. Because node 4 is publishing and subscribing to the exact same topics and services as node 3, our lower level nodes do not change at all. We don't have to rewrite a single line of our motor controller or PID code, we just don't run node 3. This saves us a bunch of time both in writing the code and troubleshooting, as we are using what we already know works. Now if we run the robot, it immediately executes a completely different strategy to solve the maze, shown here by the purple path. That is the magic of a modular robotic system. Let's see this in practice as well. Now that you know how ROS works, it's time to see it in practice, and I'm running ROS2 Humble on this Raspberry Pi 4B, and it's more than powerful enough. Here via USB cable I have connected the motor driver board that you've already seen in the PID and curve tuning videos, and also have this motor driver here. And this here dongle is for this Xbox style joystick that we're gonna use to actually control this motor. So how this all is set up is, you can see here, using just VS Code you can SSH into that IP address to which your Raspberry Pi is connected, and essentially you have full control over it. So for example, if we check the node list, let me copy that real quick here. There it goes, it bugged out a bit. But yeah, we have two active nodes, so one is motor driver communication and the other one is Xbox joystick. And you can also check the topic list. And these are the active topics that we can subscribe to or post them through nodes. So for example, if you take a look here and if we press this X button here, you can see that stuff is changing, and you can also see the color of the LED right here changed. Now it's green and now it's blue. So we are actively communicating between the two nodes sending commands. And we can subscribe to this topic here, which is the telemetry topic, as you will see start up soon. And that will show us all of the data coming from the motor driver to our Raspberry Pi, and we can monitor stuff like the voltage, current position of the motor, and so on. So let's just give it a minute to start up. And there we go. So yeah, the connection can be a bit buggy sometimes, but through VS Code, but now it works. So for example, you can see that the power supply is set to 12 volts. So if we maybe try and increase that voltage, you can see here on the screen that the voltage is now around 18.96, so around 19 volts. And we can just keep increasing and you can see how that is changing. We can also see the encoder raw position, the reduced position, and so on. So for example, if we spin the motor at 31 volts, listen to this now. You can see how fast it is spinning at this voltage. All I'm doing here is just giving it some manual commands, but we can also zero out, for example, the PID, and also let's go back to 12 volts so we don't burn out the motor, and zero out the PID, and we can try the position controller, though for some reason it's not working the best. Let's see. If you take a look, so it's a bit noisy, but we can kinda control the position, even though you can hear how rattly it is. So I'm just moving one stick and being able to control the position rather nicely. Thanks so much for watching part 2 of LM14's Robotics 101. In this video we've covered control engineering mostly, so anything from PIDs to motion profiles to the robot operating system. The next two videos will be project videos. We're really gonna make the two parts that pretty much make this, just on a bit of a smaller scale so it's easier to follow, and I'm still staying with the thing that I said in the first part. If you just have a hot glue gun and a piece of cardboard, you'll be able to follow along. So if you have any further questions or comments, please leave them down below, and hope to see you in the next video as well. See ya!